Hi class, this is Juan Ramirez with EE 2715, and in this video we'll be doing a quick description of Lab 2, which will be on January 8th, 2020. Again, we won't be meeting on Monday, January 6th, but for Wednesday when we do meet for this lab, want you guys to have the pre-lab prepared. Alright, so first we're going to talk a little bit about what this lab is about, what the objectives are, what's the background information, and we'll talk then a little bit about the pre-lab and the actual experiment that we'll be doing. So to start off the objectives, we want to look at the behavior of thermistors and how they're used to measure temperature, and also look at time constants associated with those thermistors. We're going to also become more familiar with reading electrical component data sheets. So I find a lot of value in making sure you're able to look at data sheets and determine what's really happening, what's going on with regards to determining component parameters, maximum specs, etc. The third item is to learn how to take sensor measurements and then using that data post-process to really analyze what's happening, right? So if you're doing using a sensor, oftentimes the value that you're sensing is some voltage or current that's proportional to the physical quantity you're measuring, right? So a lot of times a sensor might be a temperature sensor or a pressure sensor or a speed sensor. And those sensors will typically give you an output voltage or current that's proportional to one of those values. And so there's some post-processing that typically has to be done to find your actual speed value or pressure or, I forget the last one I said, or temperature value. Okay, so that's what the objectives are. Also, just a quick note, when you do this lab, to submit it, actually type your information and post your information regarding the actual execution of the lab into this document. So, download this document, save as with maybe your name or something, and then make sure you're filling out, you see at the top left in the header, there's a name, lab partner, date, so make sure you fill all that out. And then I'll skip a little bit of information for now, but I'll usually put in italics something that requires you to input information into the document. So if you see in pre-lab assignment task 2, I want you to go into the data sheet and identify the following parameters and type them into this document. All right, so that's what italics means is, go ahead and do something and then actually, once you've done it, take a picture or, if you did a calculation, show the calculation or show the value on this document. Okay, so a little bit of background. Thermistors are passive, thermally sensitive semiconductors that have a resistance proportional to temperature. And perhaps proportional might not be the right word, but rather that there's a relationship that's well known between temperature and resistance. Proportional might imply that the relationship is linear, but in fact the relationship is exponential, as we will talk about in a minute. So if you are trying to measure temperature for some application, for example, a good application for biomedical engineers is baby incubators or baby warmers. So oftentimes you have to check the temperature within this incubator for the newborn to ensure that they are in an environment that is healthy for them from a temperature and humidity perspective. So how do we go about measuring temperature? Well, there's 3 main ways we go about doing this, or 3 options. One is using what's called a thermocouple. So the thermocouple is essentially two different metals that are welded together at one tip, and there's a sort of physical relationship that says that between two metals they create a very small voltage based on the temperature that they're exposed to at that junction. And then you could put that thermocouple connected into a data acquisition unit, some type of measurement system that'll convert that thermocouple voltage into a temperature reading. So thermocouples are good because they are pretty inexpensive. They measure up to very high temperatures, but one of the challenges is that they're very susceptible to electrical noise being picked up and throwing the measurement off. So there's a lot of error due to electrical noise. Also, there's quite a bit of complex circuitry to convert from that voltage measured at the thermocouple to an actual temperature. So that's one way. The other way is RTD. All right, and so an RTD is a temperature sensing device that varies resistance, and that varying resistance is proportional to temperature. So this one actually, sorry. Okay. Sorry about that. So the relationship between resistance and temperature here is pretty linear. All right, so that's a good thing, because as we'll talk about with a thermistor, it's not linear. They aren't very expensive, so that's good. But one of the issues is that there isn't a lot of sensitivity. And what that means is that with a change in temperature, the change in resistance is pretty small. RTDs are made out of a certain type of metal, so they're actual metal devices that get characterized by their resistance at a certain temperature. So that's an RTD, but not a lot of sensitivity, so that's one of the challenges. Thermistors are the third more common temperature sensor options. They're actually pretty similar to RTDs in that they have a resistance that varies based on temperature. However, that relationship is exponential, which means the processing of a temperature reading is a little bit more complicated than for an RTD. However, the sensitivity is much higher. So for a certain delta in temperature, the delta in resistance and for a thermistor is quite a bit larger than for an RTD. Thermistors are based on a semiconductor as opposed to a metal for RTD, and also pretty inexpensive. Thermistors are also known for having a pretty fast response time. So that's actually what we're going to get into, is what response time means. Okay, so first, before we get into response time, let's talk about the actual relationship between temperature and resistance. So this equation here tells you what the temperature and resistance relationship is. You do, however, need what's called a reference point. So that is, at room temperature, you find what is room temperature, we call it T0, and what the resistance of the thermistor is at room temperature, and that's R0. So then what you do is, that'll give you two data points that you need. In that equation, you'll also see beta, which We don't know probably right now what it means, but essentially it's a material constant based on the type of semiconductor. So you could get different types of thermistors with different betas, usually in the range of 3,000 to 5,000. And then the final two values are temperature and resistance at some other point that's not the reference point. So that's where we are going to put this thermistor in a temperature sensing application where maybe we want to measure a temperature that is, I don't know, 50 degrees C. Right? That's what it actually is, but we want to determine that it is. So we are going to calculate what that temperature is based on what resistance you get. So in fact, you'll usually know resistance first. Some resistance, let's say 12 kilo ohms. And then you can calculate what the temperature is for that resistance, given the reference point that we just covered, and the beta value. So if we come down a little bit, we have converted that original formula into a formula here that shows what the resistance is equal to when it is in the presence of a certain temperature. Okay, so you can use either of the formulas. So now the question is, okay, well, how do I put this into a circuit to actually make a measurement? And there's a few different ways. One way to put it into a circuit is with what we call a Wheatstone bridge. That's a pretty effective way of measuring voltage across the thermistor to calculate resistance, and then from that calculate temperature. The challenge is that it's a little bit trickier to make the measurement using a Wheatstone bridge. It's actually quite easy to use a voltage divider circuit as shown below. So what you'll do is you will build this circuit where the thermistor is this guy here. Sorry. So the thermistor is on the bottom, and then you have a 10 kilo ohm resistor. Then this is a fixed resistor up top, and they're connected in series. They're connected in series to a 5-volt source. So if the thermistor at room temperature has a nominal value of 10 kilo ohms, so C0 is, let's say, 25 degrees C, R0, let's say, is 10 kilo ohms, then in that case, you have a voltage divider of 10 kilo ohms in series with 10 kilo ohms, and therefore V out would be equal to 5 times 10 over 20. Alright, so that would give us 2.5 volts. So V out would be 2.5 volts when in the presence of a 10 kilo ohm thermistor resistance, right? However, if the resistance of the thermistor changes, then V out will change as well. So that gets us into the first part of the lab. First part of the lab, or rather the pre-lab, is to start becoming familiar with the data sheet of the thermistor we'll be using. So we'll be using this thermistor part here, Murata NXFT 15XH103FA. The thermistor data sheet is attached in Blackboard. So pull it up, check out page 5, that covers some of the basic characteristics of a thermistor. So just good information to have. For step 2, I'm going to ask for a couple of the datasheet parameters. And for step 3, I want you to use your circuit analysis know-how along with the original thermistor resistance to temperature relationship to find a V out equation that tells us how V out relates to thermistor resistance, and from there to thermistor temperature, right? So essentially this is the flow of what's happening. The thermistor has a temperature. That temperature is due to the physical environment it's in. So in our case, we're going to put it, we're going to actually have it make physical contact with a warm resistor, some other power resistor, we'll call it the heat source. And so our thermistor will reach that temperature. Based on that temperature, it'll have a resistance. And to go from temperature to resistance, we have to use those equations above. And based on that resistance, we can find a V out value. And to do that, you'll have to do a little bit of circuit analysis there. So what I'm asking you to do is to find V out with respect to temperature. That's the pre-lab. Those three things. Then we will actually build two different things. One thing we'll build is a heat source. This is actually on Wednesday when we're in the lab. We'll have a heat source, and then we'll have a circuit for temperature measurement. So the heat source will be the DC power supply, connected to a power resistor. And what we're going to do is we're going to put the DC power supply in current limit to supply 1.5 amps DC through your power resistor. What should happen is that resistor, after 5 minutes or so, will reach a close to steady state value of maybe 40 to 50 degrees C. So after you've been applying that current through it, you're going to wait some time. Make sure you don't hold that resistor tightly because it'll get pretty hot. So that's one part, is we have to have a heat source that we're going to use to measure a temperature that's not the room temperature. And then for the temperature measurement, you're going to use the oscilloscope. And a circuit that you build. And the circuit will have a little thermistor attached to it. And you're going to be measuring the output voltage to see what's going on. What you'll also find, though, is that even when you connect your thermistor to the resistor, to the power resistor, the temperature, the output voltage, so you're going to actually have the thermistor touch the power resistor, the output voltage won't jump up or jump down to its final value immediately. It'll take some time. And why is that? That's due to the thermal time constant of the thermistor. So we're waiting for the heat source to reach steady state temperature. We're not looking to analyze the thermal time constant of the power resistor. We're trying to analyze the time constant of the thermistor, otherwise known as response time. Okay, so we are essentially looking to analyze response time. All right, so the first thing we'll do in the lab is we're going to identify the reference point by using a calibrated or a device to calibrate the value. So we're going to use a thermometer. And that'll allow us to find the room temperature, and then we'll use an ohm meter to find the thermistor resistance at the room temperature. Then we'll set up the heat source Again, you're going to apply a 1.5 amps DC through a 1 ohm resistor, which I'll give you guys, and you give it 5 minutes to reach a relatively close to steady state temperature value. And it'll be warm, so be careful. Now you'll use your thermometer to measure the resistor temperature after 5 minutes or so. And this will be what we call the final value, T final, and as a sort of calibration or reference point. But finally, that's when we will go ahead and build our circuit, our voltage divider with the thermistor, and then we're going to actually connect or touch the thermistor tip to the hot resistor and see how the voltage output of that voltage divider changes. And then we're going to take a snapshot of that change, and then we're going to put cursors to find 10 different data points. So, for example, your oscilloscope will show, and I think I have to, I'll do it over here. Your oscilloscope will show a voltage that maybe looks like this. So before the trace ends, you're going to hit stop so that it freezes the waveform, if you will, or stops the waveform. And then what you'll do is you'll create, I'll use a different color, you'll create a bunch of cursor values. So you're going to put a cursor here and here, so that here you have a voltage and a time point. And then you're going to do that 10 times. I'll use a different color for another point. And so on. And I would like for those points to try to be evenly spaced, ideally. And so do this for 10 points, 10 data points, up until the steady state value, or sort of the end of the stream. Record that voltage and that time in an Excel spreadsheet, and then use the voltage to temperature value or equation that you came up with in the pre-lab to convert from each V out at each data point to temperature at each data point. Alright, so that's going to be for the temperature rise measurement. And then you're going to do a similar thing, but for temperature fall measurement. And that is, we first analyzed when you apply the thermistor to the power resistor. Now we're going to apply the thermistor to the power resistor for a long time, and then all of a sudden pull it off and see what happens to the voltage, which you'll see it'll actually do something like this. Okay, it'll have a time constant like an RC capacitor voltage or an RL inductor current. And we're going to do pretty much the same steps. And now finally, you'll go and for steps 7 through 10, you'll actually do this analysis on your own. It could be outside the lab, or it could be during the Wednesday lab time, whatever you choose. But this will be an independent portion that you can kind of do without being at the lab. Okay, so I encourage you to go through these, but more importantly, just go through the pre-lab portion. And hopefully you watched through this video, maybe extended a little bit longer than I wanted to, but I want to give you a good lab 2 preparation or description. Looking forward to seeing you all Wednesday, January 8th, and we'll go from there when we see each other and actually go through the lab. All right, take care.